The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, guys, so let's get started. Welcome back from what I hope was an exciting holiday for everyone. So today we're going to talk about user authentication. And so the basic challenge that we want to address today is how can human users prove their identity to a program? And in particular, the paper that was assigned for today's class addresses sort of an existential question in the security community. Is there anything better than passwords for authentication? Right? So at a high level, it seems like passwords are a terrible idea, right? So they have very low entropy, right? It's very easy for attackers to guess them. Also, the security questions that we use to recover from lost passwords often have even lower entropy than the passwords themselves, right? Which also seems like a problem. And even worse, users typically will use the same password across a lot of different sites. Right? So that means that the vulnerability in one password, if it's easy to guess, could expose a user's activity across a wide range of sites. So as the paper for today's class states, I love this quote, "The continued domination of passwords over all other methods of end-user authentication is a major embarrassment for security researchers." Right? So the community is just seething out there. They want some better alternative. But it's not clear if there actually is an authentication scheme that actually totally dominates passwords, that's more usable, that's more deployable, that's more secure. So in today's lecture, we're basically going to do three things. So first of all, we're going to look and we're going to see how current password schemes work. Then we're going to talk about the desirable properties at a high level for any authentication scheme. And then we're finally going to look at what the paper gives us in terms of metrics for authenticating authentication schemes. And we're going to see how some of these other authentication schemes actually compare to passwords. So at a high level, what is a password? So a password is a secret that is shared between a user and a server. So the naive implementation of a password scheme is to basically just have a table, right, on the server side that essentially just maps usernames to passwords. Right? That's the simplest way you can imagine implementing one of these authentication schemes. User passes in their user name and their password. Server does a lookup in this table, compares the password that the client supplied, what's in here. If everything's good, the user is authenticated. So clearly the problem with this is that if the attacker compromises the server, right, then it can just look at this table and then get all of the user's passwords in the clear. Right? So that's clearly a bad thing. Right? So perhaps an improved solution is to have the server store a table that looks like this. So once again, it maps the username, but now it actually maps to hash of the password. Right? So the user client is going to supply their clear text password to the server. The server will then take that clear text password, hash it, do a lookup in the table, and once again see if the user is who he or she says that they are. So the advantage of this scheme is that by design, these hash functions are difficult to invert. Right? So if this table is lost, it's leaked somehow, or the attacker compromises the server, then the attacker can look at these things here, but it's difficult for the attacker to say, OK, this sort of string of random alphanumeric characters here, here's the preimage that was used as the input to the hash function to generate that value there. So that at least is the nice thing about these hashes, sort of in theory. Now, in practice, attackers don't actually have to launch brute force attacks to figure out what the preimages for these hash values are. Right? So attackers can actually take advantage of the fact that passwords, in practice, have skewed distributions. And by skewed distributions, I mean that, let's say that we knew that all passwords were 20 characters long. It's not like users actually pick passwords that sort of exist in all places in that space of 20 possible characters. In practice, people pick passwords like, 1, 2, 3, or Todd or things like this, right? And so in fact, there's been these empirical studies of how passwords work, and a lot of times these studies find things like the top 5,000 passwords cover about 20% of users. So what that means, in other words, is that if the attacker has a database of those 5,000 passwords, then the attacker can just hash those, and then when the attacker looks at this stolen password table, can just see if any of those things that come from this 5,000 large list match over here, right? And so empirically speaking, the attacker will be able to recover about 20% of passwords that way. And so folks at Yahoo found that passwords have roughly 10 to 20 bits of entropy, 10 to 20 bits of randomness in them. And that's actually not that big, right? So for example, if you think about, what might this hash function here be? So maybe it's something like SHA, something like this. So modern machines can actually calculate, millions of these hashes every second, right? So the fact that hash functions by design are supposed to be easy to calculate, supposed to be fast to calculate, combined with this fact that there are these skewed password distributions, means that in principle, this scheme here is not as secure as it might seem, right? So one thing you can imagine to try to make life more difficult on the attacker is you could imagine that you use expensive key derivation function. And so by key derivation function, I just mean this thing up here, this thing that's taking the password as an input and then generating something that's stored on the server. Right? And so what's nice about these key derivation functions is that they actually have sort of tunable cost. Right? So you can basically turn this knob and make that function run slower or faster, depending on what you want. And so the idea here is that let's say that you're going to use a key derivation function. So some of these examples are like PB, KDF2, or maybe bcrypt. You can look these up using the miracle of the internet if you care to know more about them. But the base idea is, let's imagine that one of these key derivation functions took a second to calculate, right, as opposed to a few milliseconds. That actually makes the attacker's job much more difficult, right? Because then when the attacker is trying to, let's say, generate values for these 5,000 topmost passwords, it's going to take the attacker much longer to do that. So does that all make sense how these things work? Pretty straightforward. And so internally, these key derivation functions often operate by repeatedly calling a hash multiple times. So that's all pretty straightforward. So you might say, well, does this solve the problem? So can we just use these expensive key derivation functions and be done with it? So this is a security class. Of course, the answer is no. So one problem is that the adversary can build something called rainbow tables. And so a rainbow table is basically just a map of password to hash values. And so the insight here is that even if the system is using one of these expensive key derivation functions, right, the attacker can calculate one of these tables once. Okay, it might be a little bit painful because each key derivation function invocation is slow, but the attacker can build this table once and then use that to crack all subsequent systems the attacker can break into that use that same key derivation function. Okay, so that's how rainbow tables work. And once again, to maximize the cost benefit of building this rainbow table, the attacker can take advantage of these skewed password distributions like we see up here. Right? So the attacker might only need to build a rainbow table for some small set of all possible passwords.
So salting makes this much more difficult.
Yeah, that's right. So we're going to get to salting, I believe, in a couple seconds. That's right. So, but at a high level, if you don't use salting, right, rainbow tables actually allow the attacker to spend some effort offline, calculate this table, and then sort of amortize the cost of calculating that table over breaking many different password databases. And so, right, so the next thing that we can think about to improve things is salting. I swear that guy was not a plant. I'll give you your $20 after class. So how does salting work? So the basic idea is that you just want to input some additional randomness into the way that the password is generated, right? So basically, you want to take this hash function, and you want to put some salt in there, which I'll explain in a second, and then the password. And this is the thing that you store on the server side in the table. So what is this salt? I mean, just think of it as just a string, right? A long string that's provided as sort of the first part of this hash function. Okay. So why is it better to use this scheme, right? And note that the salt is actually stored on the clear text on the server side, right? So you might be thinking, okay, well, if that salt is stored on the clear text on the server side, it seems like the server can both steal the table that maps usernames to passwords, and the attacker can also steal the salt. So why is that useful?
Because say you pick the top most common password, you can't just use it once and find any user.
That's exactly right. So basically what this does is this prevents the attacker from building a single rainbow table and then using that rainbow table against all instances of that hash function, right? And so you can basically think of this as sort of uniquifying passwords even if they're the same, basically. So this is what a lot of systems do in practice. They use this notion of a salt here. And so the best practices for this, so you want to choose a salt that's long, right? Because you can essentially think of the salt as adding more bits to this sort of pseudo password, right? And so more bits is always better. And the other thing you want to do too is that whenever the user changes his or her password, you typically want to change that salt too. So one reason for that is, let's say that users are lazy, right? And they want to pick the same password multiple times. Changing the salt will ensure that the thing that's stored in the password database will actually be different even if that password is the same. I think there was a question somewhere. Yeah.
Why is it called salt?
I'm actually not sure why it's called salt. That's a good question. I'm sure there's some answer to this, though. It's like, why are cookies called cookies? The internet will know, but I actually don't know.
It does add some taste to the hash. You know, the hash is initially something, and that's the salt. You know.
There we go. I'm glad that we're getting this on film because I feel this is how we're going to get our Turing Awards. That's right. So yeah, I'm sure there's some answer out on the internet. So I'll look that up later. But does that all basically make sense? Okay. So these approaches are fairly straightforward. All right, so what I've assumed so far is that somehow the client is transmitting the password to the server, but I haven't actually specified how that transmission is actually going to take place. So, a question? No? Okay, so yeah, how do we transmit these passwords? So, you know, the first idea you might have would be, well, we'll just send the password in the clear over the network. This is clearly cartoonishly bad, right? Because then there could be a network attacker who's basically snooping and seeing the traffic that you're sending, and that snooper can just take that password right off the wire and then impersonate you. Okay, so we always start with a straw man before I show you other straw men, which of course are also fatally flawed. So first thing you think about is sending the password in the clear. Another thing you might think, which would be a little bit better perhaps, is perhaps we send the password over an encrypted connection. Right, and so we use some type of cryptography here. Maybe there's some secret key or something like that, and that's what we use to transform the password before we send it over the connection. So at a high level, you know, encryption always seems to make things better, right? Trademark. But the problem is that unless you think carefully about how you're using things like encryption and hashing, you may not be getting the security benefits that you think that you're getting. Because, for example, what if there is someone who's sitting between you, the client, and the server, this proverbial man-in-the-middle attacker, right, who's actually snooping on your traffic and pretending to be the server, right? If, when you send encrypted data, you haven't actually authenticated the other end, right, then you could still be opening up yourself to problems, right? Because if the client just, you know, let's say picks some random key, sends it to some entity on the other side who may or may not be the server, if it's not the server, your encryption didn't really buy you anything, right? You're just sending something to some person who will then be able to get all your secrets, right? And so similarly, people might think, oh, well, what if I don't send the raw password, but I send a hash of the password instead? That actually doesn't give you anything in and of itself either, because whether you send the password or the hash of the password, I mean, the hash of the password has the same sort of semantic power as the original password itself, right? If you haven't authenticated the other side, if you haven't authenticated the server, or things like this. So the basic point with this discussion here is just to sort of stress the fact that just adding encryption or just adding hashing doesn't necessarily give you any additional power, right? If the client can't authenticate who he or she is sending the password to, then the client could be mistakenly divulging that password to someone that they don't intend to divulge it to. Okay, so perhaps a better idea than these two is to use what they call a challenge response protocol. And here's an example of a very simple challenge response protocol. So let's say we've got the client here, and then we've got the server over here. So the client says, hi, I'm Alice. And then the server responds with some challenge C, right? Some quantity that the server got to pick. And then the client is going to respond with the hash of that server sent challenge, and then you can concatenate that with the password, right? So at this point, the server can take this quantity. The server knows the challenge that it sent, right? And presumably the server knows the password. So the server can sort of recompute this quantity and see if it actually matches what the user sent, right? So what's nice about this protocol is that if we ignore man-in-the-middle attacks for a second, the server is now confident that the user is actually Alice, because only Alice would know this password here. And what's nice about this is that if the server is actually the attacker, right? So in other words, if Alice sent this thing to someone who's not the person that she's trying to authenticate to, then the attacker still doesn't know the password, right? Because the attacker got to choose C, but the attacker doesn't know what this is. And so basically for the attacker to figure out what the password is, the attacker would have to be able to, once again, sort of invert these hash functions, right? You have a question?
I'm just curious, how do we don't make the client do the hashing? How can we use JavaScript to make it do the PBK to hashing? Also increases the load in the server. And also that way the server definitely doesn't know what the password is. So it's like an extra perk that you gain.
So let's see. So your proposed scheme is that the client side is going to call this thing.
Yeah, so instead of sending the password and then having the server hash the password and check it, you'll just, the client will just send the hashed password.
The client will just send the hash password. So one thing you want to keep in mind is that you typically, well, so there's a couple of reasons. So one reason, as we'll discuss later, is that there's going to be these things called anti-hammering defenses. Right? Anti-hammering defenses are designed to prevent sort of like a bad client from continually asking, is this the password, is this the password, is this the password? Sometimes as a result, it's easier for things to be done on the server side as on the client side. But suffice it to say that you can, in fact, do the hashing on the client side, right, using JavaScript or something like this. But the basic idea is that somehow you have to have the computational expense be very, very large, right? Because that's going to prevent the attacker from just guessing sort of what the password is quickly. You have another question?
Well, I just wanted to point out that if the client does the hashing, then it is if you're not doing hashing, because your password is the hash.
So that's true, right?
So if someone gets the sort of table from the server of all the usernames and hashes, they can log in.
That's right. That's right. Yeah, it gets a little bit subtle sometimes depending on who can pick, for example, these challenge values, right? Because if clients and servers can pick challenge values, sometimes that makes it more or less difficult for the client to launch those types of attacks. So for example, like one problem with this protocol here is that basically the client doesn't get to inject any randomness into this, right? So you can imagine that we can make this protocol more difficult for the server to invert if the client actually got to choose some challenge that was put in here. So you have like a server-side challenge versus a client-side challenge. But you're right about that. Any other questions? Okay. So yeah, so this segues into the discussion we were just having. So even though to break this, the server would have to invert this hash, the attacker could still try to do one of these sort of brute force attacks. Right? So one way that we can prevent the server from doing these brute force attacks is to choose one of these expensive hash functions, kind of like we were discussing before. Another thing, as we just discussed, is that you could actually allow the client to, for example, choose its own client-chosen challenge over here. And so that essentially would act as like a client-chosen salt, right? So that would essentially make it more difficult for the hacker to do things like build up a rainbow table. Because note that if the server is the attacker here, the server always can pick the same challenge value again and again and again, right, allowing it to build up a rainbow table. But if when the client responded back, the client also included some salt, right, some client-chosen challenge that it included, then that would prevent the attacker from building one of those rainbow tables. Does that all make sense? OK. So yeah, so one thing that I mentioned is that might be useful to do is implementing these anti-hammer defenses. And so anti-hammering defenses are basically designed to rate limit the number of password guesses that sort of a bad client can issue. Right? Because the idea here is that if you've got some client who's trying to launch one of these sort of brute force guesses against a password, you don't want that client to be able to sit there in a tight loop and just say, is this the password, is this the password, is this the password, is this the password, right? So one way you can do anti-hammering is, like I said, just do that rate limiting. So the server will say, I will only accept, let's say, 3 password guesses per second from any particular client, right? You could also imagine implementing timeouts here. Right? So maybe the client can issue a bunch of password requests in a row, but then after, let's say, 10 of them are wrong, the server says, OK, you got to hold on. I will not accept any more requests from you for, let's say, 10 seconds, something like that. Right? And so both of these things are designed to prevent against brute force attacks. And so, for example, like some smart cards have these types of defenses. Some TPMs have these kinds of defenses, right, to basically stop against this brute force attack. So why is it important to use these anti-hammering defenses? Well, one reason why it's important is, as we discussed, these passwords have so little entropy, right? So because passwords typically have so little entropy, it's really important to prevent the attacker from just trying to cycle through that low entropy space very, very quickly. So as you may be aware, a lot of websites have these formatting constraints that push upon you for your passwords. They'll say things like, oh, your password must have, an unprintable, not an unprintable character, but it must have like a punctuation. It must have a mixture of numbers and letters. You must have like uppercase and lowercase stuff, so on and so forth. And so what those constraints are trying to get you to do is they're trying to get you to expand the entropy of the password. But what's problematic, though, is that it's not really these formatting constraints that we should be caring about. It's the actual entropy of the password itself, right? So as it turns out, even if people are given these constraints, like you have to use punctuation characters and stuff like that, the entropy of the resulting passwords is often quite low, right? So for example, people will often put punctuation at the beginning or the end because they don't want to be troubled to remember, like, do I have like a $ in the middle of something, right? And so as it turns out, these formatting requirements oftentimes don't make dictionary attacks much harder for a sophisticated adversary. Right? And the reason is because basically the dictionary attacker can leverage these observations about how people pick passwords even in the presence of constraints. Right? So for example, if the attacker knows that people typically put punctuation at the beginning and the end, just incorporate that into your dictionary attack. Right? And so there's actually a really interesting website you can go to that's called Telepathwords. And so what's neat about this site is that you can it has a little text box, right? You can type a character into that text box. You're pretending that you're entering in a password. And Telepathwords will try to guess what your next character is, right? And so like as you type additional characters, it'll have a little drop-down box which says, were you going to put this? Were you going to put this? And it'll give you a little, like a little blurb that says, here's why I think that you were going to enter this next password. So how does Telepathwords work? So it basically has a bunch of databases, right? It has a database of common passwords. It also has a list of popular phrases that it's taken from websites. And then it also has this set of heuristics which describe common user biases in picking passwords. So for example, one funny bias is that people will often, like when they're forced with these constraints to say you must use punctuation and stuff like that, a lot of times they will, when they're picking characters for the password, they'll use keys that are adjacent to each other. Right? So in other words, there'll be very small edit distance in physical space with respect to edit distance sort of in the actual password itself. So what Telepathwords does is it has this big database here. So when you type in things, it's running these models and it's saying, statistically speaking, here's the most likely thing that you're going to type next. It's almost like autocomplete for passwords. All right? And so what's funny is that this shows, once again, that if you have these constraints, they actually don't protect you that much if there are still these underlying sort of a priori distributions of things that the attacker can leverage. I think there was a question.
Yeah. So it seems like if an attacker is too sophisticated, that they could, try guessing like the user's password from a bunch of IP addresses and things. And the only way to sort of prevent hammering in this case would just be to have like a global rate limit on password to the user's account.
Yeah.
But then you have like this issue of like, DOS possibility against the legitimate users who want to log in. So how do you like balance?
Yeah, it's very tricky. No, that's a good point. So anti-hammering, I mean, it basically gets down to what's the scope of the attack that you're trying to prevent, right? So if you're concerned about sort of distributed attackers in sort of a network system, it does become very, very subtle. And suffice it to say that the notion of anti-hammering in distributed systems, and also the notion of things like, let's say, click fraud, for example, so in other words, how does someone who's running an advertising campaign online determine if someone's actually clicking the link and I should actually be paying someone for those clicks versus this is just some spammer who's got some bot that's just sitting there clicking on stuff, right? So suffice it to say there's a lot of distributed heuristics that try to solve those problems. And in many cases, it's not a science, it's an art. But you're exactly correct that in the distributed setting, things get much more difficult. All right, so does this all make sense? Yeah.
The cryptographic anti-hammering defenses. Most of the time you're not sending a hash on the line, and these hashes are at a pretty high rate. And what you get out of it is exactly what you need. You get either the password or the hash of the password. So is there, like, I know there are protocols like SRP, or there are some zero knowledge protocols.
Yeah, so they do. Those things are, so yeah, those protocols provide some stronger cryptographic guarantees. A lot of times they are not backwards compatible with current systems, which is why in practice you don't see them used a lot. But yeah, so there are some protocols, for example, that that allow the server to not have sort of any notion of the password at all, right? So there's some zero knowledge type thing or whatever. So those things do work in practice. But like one of the things that this paper says is very interesting is that they basically go through all these authentication schemes and they say, okay, here's passwords, yeah, they kind of suck. Here's some other things that are actually much stronger on the security axis, but then they all fail on like deployability or usability or things like that. And so that's sort of one of the interesting and slightly sad outcomes of this paper, that maybe even though we have all these sort of much stronger from the security perspective protocols, we can't deploy them for some usability reason or some sort of technical reason. Okay, so that's just a fun site to go to, right? And so they claim that they don't store your passwords, so you can take them at their word if you want to. But it is very interesting to just sit down and think, like, what password would I generate, and then type into this and see how accurate it is in guessing what the next thing will be, right? And it even covers things like the popular heuristic, like take a popular phrase and then that has multiple words, and then only take like the first letter of each word. So this thing is very, very good, very, very scary too. Okay, so that's Telepathwords. And so one thing that is also interesting to think about is, in your password scheme, is it vulnerable to offline guessing? Right, so this was a problem that Kerberos v4 had, and then also v5 without this thing they call pre-auth. So the basic idea was that in these versions of Kerberos, anyone could ask the KDC for a ticket that would be encrypted with the user's password, right? So basically, the KDC did not authenticate requests that were coming from a client. Now, the thing that the KDC would return was, in fact, there was some set of bits here that the KDC would return. I'm sure you don't want to think about this ugly set of cryptographic primitives anymore, but suffice it to say the KDC would return this stuff that was encrypted with the key of the client, right? That's what will come back to the client side. So the problem with this is that because the server did not check who it was sending this encrypted set of things to, the attacker can basically get this thing here and then try to just guess what KC is, right? Just guess that KC is some value, try to decrypt this, see if it looks reasonable. If not, try to guess another KC, decrypt this, see if it looks reasonable, right? And the reason why the attacker can launch this type of attack is that this thing here, this TGT, actually has a known format. So it has things in here like timestamps, and it has things in here like various length fields which have to be sort of internally consistent. And so that basically helps the attacker, right? Because if the attacker guesses a KC, gets this thing here, a decrypted thing, and the internal fields don't check out, the attacker knows that it picked the wrong KC, so they can go on and pick another KC, right? And so in Kerberos v5, basically the client has to send in this thing that it sends over to the KDC, it basically sends a timestamp, and then this timestamp is going to be encrypted with KC, right? So this is sent to the server, and the server looks at this and validates that before it will send something back to the client, right? And so that gets rid of this problem that any random client can show up and just ask for this thing here. All right. Yeah.
So is the timestamp included in the message? So can't an attacker just get this message and brute force it?
Let's see here. So can't the attacker get this message here?
Yeah, the encryption, the ciphertext.
So you're worried that an attacker might try to spoof this, for example, or?
No, I just brute force it and get KC out.
Okay. So in other words, you're worried someone could observe this. The attacker could observe. Right. So I believe that this is put inside an encrypted thing that belongs to the server, that the key belongs to the server, I think, to prevent that attack. I have to check the protocol, so don't quote me on that. But you're correct that if it's not, for example, and if the attacker, for example, knew something about what the current time is, roughly, that actually is super useful, right? Because then the attacker can guess, oh, the timestamp should be roughly between here and here, right? And if it sees this in the clear, it can do the exact same attack that we had up here.
It's a little better because the attacker has to be in the middle, but it's still susceptible.
That's true. Well, yeah, that's right. I mean, the attacker has to be on the network somewhere sniffing stuff. That's right. All right, so that's offline guessing. So another thing that's important to think about is sort of password recovery. So this is the idea that you lose your password, and then somehow you have to go to the service and you have to ask for another password, right? But before you get that password, you have to prove that you are you in some way. So how does that work? How do you do password recovery? So what's interesting is that people oftentimes focus on the entropy of the password itself, right? But the problem is that if the password recovery questions or the password recovery scheme has low entropy, that actually affects the entropy of the overall authentication scheme, right? So in other words, the strength of the overall scheme is basically equal to the minimum of the password entropy and the recovery question entropy. And so you see this actually play out in a lot of real-world scenarios. There's a lot of famous cases, like the Sarah Palin case, where basically someone was able to recover her password fraudulently because her recovery questions were things that any random person could find by looking at her Wikipedia article, for example, find out where she went to high school and things like that. And so oftentimes these password recovery questions are not very good. And they're not very good because of a couple of reasons. So sometimes these things just have very low entropy, right? So if you have a password recovery question that is something like, what's your favorite color, right? The most popular answers are going to be like blue and red. Nobody's going to say like off-white, fuchsia, magenta, right? So some of these recovery questions just intrinsically are just very difficult to provide a lot of entropy for. The other problem is that so sometimes these recovery questions can be leaked via social media. So for example, if one of the recovery questions is, what's your favorite movie? So maybe the space there is a little bit bigger. But if intrinsically I can go look at, let's say your IMDb profile, your Facebook profile, and figure out like, oh, hey, you literally told me that's your favorite movie, this isn't super useful either, right? And another problem, this is actually sort of the funniest one, is that the user-selected recovery questions are often super weak. So for example, people have done a survey of what some of these questions look like, and sometimes users themselves will set recovery questions that are things like, what is 2 plus 3? Right? And so that's, at the time, the user's thinking this is a big hassle, never going to have to use this, but trivially, most humans who pass the Turing test can answer that question successfully, and then therefore get the user's password back.
So both Microsoft and Google have a scheme for recovering passwords that doesn't use any recovery passwords for recovery questions. It's basically you enter in your name and maybe the subjects of some emails that you've sent, with a small amount of additional information. Based on that, in some cases they can So
that's right.
The security of that kind of stuff then
So I don't know of any formal study like that. Those things are actually a lot better. So I actually know this because I was trying to help a friend go through this process. So she basically lost control of her Gmail account, and she was trying to prove that this was her account. And so yeah, they would ask you things like, roughly speaking, when did you open this account? Roughly speaking, before you lost control of this account to Hezbollah or whatever, who are some of the people that you talk to? And things like that. And it's actually a pretty laborious process, right? But what ends up happening is that you're exactly correct. It ends up being much more powerful than this stuff, right? And so, like I said, I don't know of any formal studies of that, but it does seem, at least intuitively, to be much stronger than these types of things. All right, any other questions? Okay, so yeah, so now we can get to sort of the paper for today. So in the reading for today, the authors basically propose a bunch of factors that can be used to evaluate these authentication schemes, right? And what's really cool about this paper, I think, is that it basically tries to say, look, a lot of us in the security community are sitting there kind of fighting, just based on aesthetic principles. We should pick this because I just like the way that the curly braces look in the proof. We should pick this because it just uses a lot of math mode, right? And so what they say is, well, look, why don't we try to establish some type of criteria? Maybe some of the criteria are a little bit subjective, but let's just try to have this taxonomy of ways to evaluate these authentication schemes. Then let's just see how these various schemes stack up. And so the authors basically propose 3 high-level metrics for evaluating these schemes. So the first metric is usability. And so the base idea here is, how easy is it for users to interact with this authentication scheme, right? So they define a couple interesting properties. So for example, is it easy to learn? This basically just means, is the scheme easy to learn, right? So some of these categories are pretty straightforward. Some of them actually involve a little bit of subtlety, but this one makes a lot of sense. And so if we look at passwords sort of pass this test, right? Because everybody is used to using passwords, so we'll say that they're easy to learn. Another category is infrequent errors. So that means when you are trying to authenticate to the system, if you are the actual user in question, is it the case that you can often authenticate yourself without generating errors? And so here, the authors say quasi-yes. And so the quasi prefix is one of the more entertaining aspects of the paper, right? Because the authors kind of admit there's this element of subjectivity to it, so we can't necessarily say with crisp precision, yes, no, things like this. So the reason why they say quasi-yes is because in general you can authenticate with a password successfully. But we've all been in that place where it's like 3 a.m., we're trying to log into our email server, our mind's not in the right place, and we enter a bunch of errors a bunch of times, right? So they say quasi-yes for this. Another category is scalable for users. And so the basic idea here is, if the user has a bunch of different services that he or she wants to authenticate to, does this scheme sort of scale well, right? Does the user have to remember some new thing for each one of these schemes? And so for here, the authors say no. Right? Because in practice, it's very difficult for users to remember a separate password for every single site that they go to. This is one reason actually why people reuse their passwords often. So another usability property is easy recovery. So what happens if you lose your authentication token, in this case your password? Is it easy to reset? And in this case, the answer for passwords is yes. In fact, they are probably too easy to reset, as we just discussed a couple minutes ago. So that's a yes. And so another interesting one is nothing to carry. So a lot of the more Baroque authentication protocols require that you run some smartphone app, or you have some security token or a smart card or things like that. So that's a burden, right? Maybe not with a smartphone so much, but having to carry around one of these other gadgets is probably a pain. And so this is actually one nice feature of passwords. You basically only have to carry around your brain, which presumably you should have at all moments. So that's basically what usability looks like, right? And it's just very interesting at a high level that a lot of times, these sort of factors are given a little bit of a short shrift in the security community, when people are evaluating new schemes. They say, oh, this thing uses like 1 million bits of entropy, and it can only be broken by the Death Star or whatever. But then people don't necessarily remember, oh, these are actually very important factors too, right? Okay, so the next sort of high-level category that the authors use to evaluate past authentication schemes is deployability. So the base idea here is how easy is it to incorporate this system into current web services, right? So one thing that they look at, for example, is it server compatible? And this basically means, can I easily integrate this scheme with today's servers, which are based around sort of text-based passwords, right? And so since success here is defined with respect to passwords, passwords succeed. So another metric is browser compatibility. Similar type of thing. Can I use this scheme with current off-the-shelf browsers without having to install a plugin, something like that? Once again, passwords win by default. And another interesting one is accessibility. So can people who can use passwords now, but maybe have some type of physical disability, maybe they're blind, or they can't hear well, they can't gesture well, or things like that, can they actually use this scheme, right? And this is actually pretty important. So once again, the authors say yes. It's a little bit weird because it's not clear that all people with all disabilities can use passwords, but they say yes here. So these are sort of 3 interesting things to think about with respect to deployability. And the reason why this deployability category is so important is because it's very difficult to get anyone to upgrade anything ever, really, right? I mean, people don't even want to reboot their machines to get a new OS update installed. So it's very difficult if a scheme requires reasonable changes on the server to sort of get people on the server to actually do different stuff. This gets back to your question, why don't we use these better things? Because deployability in many cases is super, super important to people. All right, so then the final category that people look at is security. Right, so what kinds of attacks can this scheme prevent? So a lot of these security properties are sort of resilient to foo, right? So I'll just sort of shorten that with res. So is the scheme resilient to physical observation? Right? So the idea here is that an attacker cannot impersonate a user after observing them authenticate a few times. So imagine that you had a shoulder surfer, so you're somewhere in a computer lab, someone's looking over your shoulder, seeing what you type in. Imagine someone's videotaping you, maybe someone's got a microphone, they're listening to sort of like the acoustic signature of your keyboard and trying to extract things from that, so on and so forth. So the authors say that passwords actually fail this test, and that's because if someone can videotape you typing in things, they can pretty easily figure out what letters you typed. Or there's actually these attacks where you can actually listen to the acoustic fingerprint of a keyboard and detect what was typed based on what sounds that you hear. So passwords are not resistant to physical observation. So another property is resistant to targeted impersonation. And so the basic idea here is that, is it possible for someone who knows you, a friend, an acquaintance, a spouse, a loved one, a family member, whatever, to impersonate you using their knowledge of who you are and what you do, right? So could your friend try to pretend to be you easily in this particular scheme? So here, the authors basically have another one of these quasi-yeses. And they say quasi-yes because they're not aware of any studies which show that if you know a person, you're more likely to be able to guess their password. So they say quasi-yes for that. And so note that resistance to targeted impersonation, this is where most security backup questions fail miserably, right? Because if someone knows something about you, quite easily they can sort of guess your security questions in many cases. All right, so then we have two categories that involve guessing. So the first one is resilient to throttled guessing. And so what this means is if the attacker cannot issue guesses at line rate, because, for example, the server uses anti-hammering mechanisms, is the scheme safe against the attacker, right? And so here they say no, right? And so the reason why they say no is because in practice, passwords not only have sort of low inherent entropy, right, because they're not that long, but also they have that skewed distribution, right? And so what that means is that even if the attacker is throttled in some way, typically the attacker can still make good forward progress and crack a lot of people's passwords. So they define another guessing property, which is resistant to unthrottled guessing. And so this is basically saying, suppose that the attacker can issue these authentication forgery requests as quickly as he or she wants, right? So in other words, the attacker is only limited by the speed of their hardware. So is the authentication scheme resilient to that type of attack? And here, this answer is also no, for the same reason that the answer was no up here. So basically, passwords have a very small entropy space, and they come from the skewed distribution. So that's all pretty straightforward. One interesting one is resiliency to internal observation. So this means that the attacker cannot impersonate a user by intercepting that user's input. For example, by installing a keystroke logger on the keyboard that the user is using and using that logger to steal key presses, right? This also means, for example, that there's no way for a network attacker who's observing the things that the client's sending over the wire to use that knowledge of the network traffic to later impersonate the user. And so here they say passwords do not have this scheme. And they essentially say it's because passwords are static tokens, right? They don't change. And typically static tokens are vulnerable to replay, right? So if somehow, for example, an attacker installs a keystroke logger and gets your password, then basically the attacker can use that password until it's either expired or revoked or something like that. It can just replay it again and again to that authenticating server on the other side. So here passwords actually fail that test. Another thing that we've talked about a little bit in this class, phishing. So resilience to phishing is another security metric. And the basic idea here is that if the attacker can simulate a valid service, for example, by attacking the DNS infrastructure or something like that, then the attacker cannot collect credentials from the user that the attacker can then use to pretend to be the user later on. And so this basically is supposed to penalize sites that do not strongly tell the user, hey, I am this particular service, so you can feel confident to give me your credentials. And so here passwords fail just because phishing sites are very, very popular. So passwords don't really intrinsically provide any protection against that. Now the next two are particularly interesting in the context of a large-scale distributed system. So no trusted third party. This essentially means that other than the client and the server, there's no one else in the system that is sort of involved in the authentication protocol, right? And so that means that there's no third party who, if that third party were compromised, the entire integrity of the security scheme might fall apart. And so this is actually an interesting property to look at, because a lot of authentication problems would go away if we could just store all of our authentication information in one place. Right? We just store it in one place. It's very simple. We don't have to remember a lot of stuff on the client. We just say, whatever service you want to use, you always go to this one third party, and that third party will also always be able to sort of authenticate you and then allow you to go on your merry way. Now, of course, third parties are problematic from the perspective of robustness, right? Because if you do have one of these global third parties that everybody trusts, if that third party gets subverted, then perhaps the integrity of all the sites that use that third party to authenticate, all those sites are potentially in danger. So they say that passwords do not have a trusted third party because each user is forced to have a separate password for each site. A related property is resilient to leaks from other verifiers. And by verifiers, they just refer to these services that you're authenticating to. And so the authors define this as nothing that a service could possibly leak can help an attacker impersonate the user to another service. So this basically penalizes schemes where fraud or malice or incompetence at one particular service will then possibly result in leakage of your credentials at some other service. Right? And so this property is actually related to the no trusted third party scheme, right? Metric. Because if you don't want to trust the third party, then automatically you start thinking we want some type of distributed authentication system. Right? But the problem with that then is that you may end up with a situation where the overall security of the scheme is dependent on the security of the weakest link. So think once again like HTTPS, like the certificate authorities, right? In a certain sense, that's the distributed authentication system, right? But the problem is that if one CA gets subverted, then that means that person can issue sort of fraudulent certificates for a bunch of different parties, right? And so if the world ever makes a mistake and gives CA power to someone who's untrustworthy, then potentially the whole thing can fall apart. And so the authors say here that this is a no for passwords. So they say that because people often reuse passwords across the same site, if let's say my Gmail password's stolen, then maybe that means that my Facebook password has been stolen too. So the authors give a no there for passwords. So this is just sort of an overview of some of the more important categories that the authors look at. And so, sort of these things are only useful when you compare them to the scores that some other system might have gotten. So one interesting system to compare against is biometrics. So biometrics, at first glance, seem like a super cool thing to do, right? And so in fact, like a lot of times, like when you go to watch science fiction movies, everybody's looking in iris scanners and like putting their fingers in some type of palm reader, things like that. Seems very futuristic, right? So basically, biometrics leverage the unique aspects of someone's sort of body or the way that they gesture, things like that, to authenticate the person. And so one thing that might be interesting to think about is how big is the key space? Actually, I'll put this over here. So the key space is actually not as big as you might think that it would be. So for example, for fingerprints, the key space is roughly 13 bits. If you look at iris scanning, the amount of entropy is roughly 20 bits. And if you look at voice recognition, then you'll see that the amount of entropy is roughly about 12 bits. And so this seems perhaps a little bit concerning in as much as we have all these hopes that biometrics are from the future and they're going to really help us. But when we look at how much entropy they have, they actually are not that much better than passwords. Actually, they're roughly equivalent, because if you remember, passwords have roughly 10 to 20 bits of entropy, right? So that's a little bit disturbing, but whatever. We'll continue, and then we'll eventually see how biometrics stack up versus passwords. And so how do they stack up? So according to the authors, biometrics are easy to learn. And that's because presumably you know how to move your body around or look at things in an iris scanner. Okay, question?
So are those numbers from like the limitation of technology scanning fingerprints, or are they just a fundamental property of fingerprints?
So I believe that they are, well, let's put it like this. So I think that current hardware, like current authentication hardware, gives you these limits here. I think that if you had higher resolution biometric scanners, you could potentially get better. I mean, presumably there's some lower limit that's guaranteed by like, the uniqueness of your DNA or things like that. But yeah, I think these are not fundamental limits. So yeah, so the authors say that biometrics are easy to learn because it's pretty easy to use these biometric scanners. What's interesting is that biometrics have frequent errors, right? And that's actually a bit problematic if any of you have ever tried to use these things. So like, for example, like vocal recognition. So like if you have a cold or your voice is a little bit hoarse because you've been yelling at a concert all day or whatever, these things actually fail fairly regularly. So biometric scores a no on this. Scalable for users, so this is a yes, right? Because basically you just bring yourself, right, to whatever service you want to authenticate to, and then you can just sort of authenticate like magic. So that's a very nice property. With respect to ease of recovery, so this is a no. And this is actually one of the big problems with biometrics, right? So let's say somebody somehow manages to steal your iris scan, for example. That person can replay that arbitrarily. Like you can't get new eyes. So that. Not yet. Yeah, exactly. That's right. Yeah, not with that attitude. Yeah. So yeah, until getting new eyes is something Amazon.com will sell, easy recovery is actually a pretty big problem here. And then for the nothing to carry, right, biometrics wins because you just carry all this stuff with you automatically. Okay, so then what about deployability? So for deployability, this is actually not a big win for biometrics, right? So it is not server compatible. It is not browser compatible because browsers don't have some native API for taking in iris scans or things like that. And in terms of accessibility, the authors say this is a quasi-yes. And I think they say quasi-yes because they say that because biometrics are error-prone to enter, that this kind of makes it difficult even for sort of regularly able people to use. And then if you have some physical impediment, it makes it even more difficult to use some of these schemes, right? So, okay, so that's a little sad. So biometrics don't quite seem deployable. So what about on security? So are they resilient to physical observation? So here we will say yes, in the sense that if someone observes you using an iris scan, for example, or someone observes you using a fingerprint reader, presumably that does not then give them the ability to impersonate you. Maybe like voice recognition is a little bit different, but we'll just say that we'll be charitable, and we'll say yes here.
But isn't that very weird? Because they're actually weaker than that. You don't even need to be observed while you authenticate. You can just be observed in real life. Like if I take a very good high-resolution picture of your iris, or I look at your milk glass, I can get your fingerprint.
That's right. That's right. Never leave a milk glass around this guy. Yeah, so no, that's actually a very valid point. And so with like a lot of these ratings, this is why I think the authors go to such pains to say, look, we don't want to assign weights to these things. And they say, we have this methodology whereby it's like, if we were doing this, like you would come up with a rating, then I would sort of cross-validate it, does it make sense with me, and so on and so forth. But you're right that there's a lot of wiggle room and stuff like this. And this is one reason why I think some of these quasi-ratings are even more funny than they should normally be. Because intrinsically, we're sitting around, we're sort of debating, like, what does it mean to physically observe someone, for example. So yeah, you gotta take all this stuff with a grain of salt. All right, so resistant to targeted impersonation. So here they say no, and this is actually for the reasons that you were just discussing, right? So they say that if I want to particularly impersonate you, I will go find your milk glass, I will take off your fingerprints with tape, and then take it back to the crime lab and then do whatever criminals do. So they say no. here for target impersonation. Now, with respect to the guessing metrics, so this is about interesting. So they say that biometrics are resilient to throttle guessing, but they are not resistant to unthrottled guessing. The reason they say this is because, let's look at this one first. So if the attacker basically is not thwarted by these anti-hammering defenses and can just sort of issue guesses as quickly as he or she wants, then remember that the entropy space for these biometrics is actually not that large, right? So if you have someone who can do unthrottled guessing, we say no, biometrics are actually fairly weak, right? However, the authors say that they are resistant to throttled guessing, and the reason for that is because biometrics, even though they have sort of an intrinsically small entropy space, they're actually more randomly distributed within that entropy space, if that makes sense, right? And that's different than passwords, right? Because passwords both have a small entropy space, but they're also clustered within some region of the entropy space, which makes things even worse. So does that all make sense? Yeah, okay. And then resilient to internal observation, here they say no, and that's because if someone manages, for example, to corrupt your fingerprint reader or whatever, and somehow gets access to your fingerprint token, that is essentially a static secret, right, which can be sort of replayed arbitrarily. Resistance to phishing, here they say no. No trusted third party, so that's a yes. And then this one's actually interesting. So the resilience to leaks from other servers, here they say no. And this is very similar to why passwords are not resilient to this. Because once again, your biometrics are a static token, right? So if I use my iris scan to authenticate to Amazon.com, and then Amazon.com leaks that iris scan data, then someone can now impersonate me at, Facebook or something like that, some other service that uses that data. All right, so what does this mean? We have these two columns filled with no's and yeses and quasi-yeses and stuff like that. So one way you could interpret this is just one way, right, is we could say, all right, what if we were to sum up all of these values here? Okay, so let's say for each yes, we actually gave a scheme, let's say 1 point. Let's say for each no, we gave it 0 points. And then let's say for each quasi-yes, we give it 0.5 points. Okay, just to be clear, this is not totally arbitrary, it is almost totally arbitrary, right? But this is sort of part of the interesting exercise of trying to understand what this paper is trying to tell us, right? So let's say that we have that scheme, right? Yes equals 1, no equals 0, and then quasi-yes is 0.5. So what do the scores end up looking like? So we end up seeing that passwords get an 8, and we see that biometrics get a 6.5. Okay, so I mean, we now have two numbers. So what does this mean? Well, I think in these numbers are very interesting. I feel like I've invented a new type of number, which is like a qualitative number, right? So what does this mean? Well, as the authors go to pains to express, they actually don't want to assign weights. They don't actually want to sort of do this comparison. But the reason why I think this is useful, at least, is because you can at least see that it's not like biometrics blow passwords away. Right? It's not like they're just sort of like just so much better that obviously we should move towards biometrics instead of using passwords, right? And that's really the point of that big table that the authors give in the paper, right? That's in fact why they don't give numbers. They just want to say, if you blur your eyes and you look at this table, you'll see that like passwords are good in some things and other things are good in better things, and then so on and so forth. So ultimately what it comes down to is, in your particular security situation, which one of these factors do you care about the most? And which ones are you willing to sort of sacrifice, right? So once again, this score, you shouldn't take this too literally, but this is just saying, well, both of these things have strengths, both of these things have weaknesses. All right, so basically we went through this exercise and we figured out that it's very difficult to say that, one authentication scheme is totally dominant over another authentication scheme. So you might think, all right, well, maybe we can sort of have the best of these sort of ambiguous worlds by somehow combining multiple authentication schemes. And that is what is done in systems that use multi-factor authentication. And so the idea here is that you want to use defense in depth. So the basic idea is that you want to require users to authenticate themselves with 2 or more different authentication mechanisms, right? And the key is that each one of these mechanisms should use different modalities. And by different modalities, I mean they should leverage different sort of ways of authenticating. So for example, one of those mechanisms might leverage something that you know. So this is, for example, a password. Another modality might leverage something that you possess. And so an example of this might be a cell phone, maybe a smart card, something like this. And then maybe another modality will leverage something that you are. And so this is, for example, what's done by biometrics. And so the idea behind this multi-factor authentication is that when you use schemes like this, an attacker has to sort of steal or subvert multiple things to be able to successfully impersonate you. So for example, the attacker might be able to guess your password, but maybe the attacker can't steal your cell phone, for instance. And so there's a couple different examples of this. Maybe the most common one is Google's 2-factor authentication for things like Gmail, for example. So you have a password, but then when Google detects that you're using, let's say, Gmail from a machine it doesn't know about, it's going to send you a text message and has some little code in there, right? And then you have to type in that code as well, and Google says, okay, well, presumably you weren't so clueless that you got your password stolen and someone stole your cell phone. If that happened to you, you deserve to get hacked. So Google's a good example of this. AWS actually has this too, Amazon Web Services. So you can actually use 2-factor authentication to control your VMs or things like that. And they have an option to use a smartphone app for the second thing in addition to the password. They also allow you to use like a custom security dongle that's dedicated hardware that just allows you to sort of do this 2-factor authentication. So this all seems very nice. One sort of sad thing, though, is that I didn't put an S on. How do you spell possess? This is embarrassing. Let's just move on from there. So one thing that is a little bit sad about this stuff is that there are actually empirical studies that show that if you give users a second means of authentication besides passwords, then they will typically pick weaker passwords, right? Because they then get more confidence that they now have these 2 things. So why not I just make my password, Mr. Rogers, and then just be done with it? So there's interesting sort of models that security researchers have about how people sort of evaluate risk. So it's interesting. So the more protections you give them, sometimes the weaker they will use other protections.
I always thought like that with like the ATM idea that you have a credit card and they're like, so that means your PIN can be 4 numbers, which is totally not guessable by anyone, right?
Yeah, I mean, credit cards are very interesting because, yeah, they allow you to have these 4-digit PINs. But then, like, behind the scenes, they have these enormous, like, fraud prevention sort of setups that are actually extremely interesting, like the machine learning they do and stuff like that. I mean, I don't know if you've ever been in a situation where, like, you go overseas, for example, and you try to use your card. Like sometimes, at first I thought it was like Liam Nielsen on the other end. Like someone will call me, it's like, are you using your ATM card? I'm like, yes, I am using my ATM card, what's going on? And it's like the bank, right? And so like that's a very easy thing for them to detect, right? You're actually using your ATM card internationally. But sometimes, like I've actually had that happen to me where I went to a website, like an e-commerce site, that I hadn't been to before. And for whatever reason, they thought it was outside my profile. Right? So maybe I usually buy science fiction books, and then all of a sudden I buy a My Little Pony book, and then they'll call me or they send me an email. And they're like, if you don't get back to us in 30 minutes, we're going to put a lock on your card. And so I think the reason that credit card companies do that is because they really feel this tension between wanting people to use credit cards, because that's how they make money, right? Versus not wanting criminals to use the credit cards, that's how they lose money. So they sort of have decided to sort of err on the side of putting a lot of security on the back-end infrastructure, doing the machine learning and stuff like that to sort of analyze fraud-like patterns. Any other questions? Okay, so in the homework question basically asks you to think about, what are some of the potential factors you might want to consider when you're thinking about authentication schemes in a bunch of different scenarios. And I mean, at a high level, there's no sort of right or wrong answer to the homework question. It's very much like this discussion here, right? You sort of look at a bunch of things that you could be concerned about, and then you decide, okay, well, in this scenario, I care more about this. In this scenario, I care more about this. So for example, one of the questions was about logging into a public Athena machine. What might you want to care about there? Well, maybe one thing that you might care about, but that might be difficult to protect against is sort of resistance to internal observation, right? Because maybe there's a lot of malware possibly on those machines. I mean, who knows, what these undergrads are doing, right? So maybe it's difficult to protect against that. Maybe you have to punt on that. Another thing you might think about is, with respect to that, maybe that means that biometrics isn't a great idea. So a lot of times biometrics, you really want to have that biometric reader be something that you trust, right? Because once again, it's very difficult to replace your iris scan. It's very difficult to replace your fingerprints. So, if you think that you're in a situation where you can't guarantee this property, then maybe biometrics is a bad idea, because the penalty for losing someone's, fingerprint data is actually pretty bad. Now that person will always be on the, no-fly list, because their fingerprints are always considered to be terrible. So, getting back to sort of the ATM example, so what kinds of things might you care about there? Well, there it's a little bit of a different threat model, I think. So to the banks, ATM security actually matters a lot. So for example, one thing they want is resistance to physical observation. So this is the idea: if I see you somehow interacting with the ATM machine, I shouldn't be able to use that and then somehow impersonate you. All right? And then they also want this resiliency to theft too. The idea, like, if I lose my card, then it shouldn't be the case that someone can just take my card and then use it to buy things on my behalf. And that gets back to our previous discussion. The credit card companies have decided to say, we're going to actually implement a lot of the heavyweight security stuff on our side in exchange for making it easier for you to spend money and then forget to pay your fees, and then we get more money that way, right? But they do definitely care about those things. One thing you might think about, once again going back to biometrics, is, does the bank trust ATMs? Like, does it actually trust those physical terminals? So on the one hand, you might think yes, because presumably the banks either built them or they trust who built them. But on the other hand, it's like, once those things get out in the wild, like, only Zeus knows what's going on, right? And in fact, it's a pretty popular scam in a lot of countries to have sort of like fake ATMs, or to have sort of like shell ATMs. You go into a country, you go into the ATM, you put your card in there, and either does like a relay attack, or it actually doesn't ever talk to the bank back in at all. It just has a reader which steals your PIN, right? So maybe in fact the banks don't trust those end terminals. And if that's the case, once again, maybe biometrics are not a good idea, even though you'd think that that seems kind of like a good idea. I can only withdraw money if my biosignature matches. And another interesting thing to think about is, maybe there should be, in the ATM case, sort of two different levels of security based on whether I want to just read the state of my account or whether I want to maybe write. And by write, I mean like actually spend some money, right? So maybe it makes sense, like if I just want to check how much money I have, maybe just a password or just a PIN is good enough for that. But then maybe if I want to actually like withdraw some money, maybe we use some two-factor authentication scheme. Maybe something gets sent to my phone, or maybe something like that. Like, I know, like, once again, in sort of the overseas scenario, or if you're somewhere where you don't necessarily trust that terminal, it can be nice to have that two-factor authentication protecting your transactions, right? Because maybe you don't care if the criminal reads that you have some, X number of dollars in the account, but you don't want them to actually change that either which way. All right, so what's interesting is that, you get to the end of this paper, and, in a sense, it's kind of like watching Inception. You're kind of like, I feel both happy and sad. Like, that was a weird ending, because on the one hand it says, well, here's this nice framework for evaluating stuff, right? As it turns out, these schemes, like, they don't nicely cluster, right? In terms of like, here's everything that is better, and then here's everything that is worse. And so the conclusion, I think, of the paper is that, well, this authentication scheme that you should use is actually highly dependent on your particular situation. And so I think one great example of that is this thing. They don't mention this in the short version of the paper, but they mention this in the longer version of the tech report. It's this thing called the cap reader. Right? And the reason I thought that was interesting is because if you look in the short version of the report, it says there was only one thing that got total dominance on the security questions, right? That just went all the way through. It's like, yes, yes, yes. It's the cap reader. We don't talk about it in this short paper. I was like, So I went over, I read the longer version. So what is the cap reader? So basically it's a way to basically protect online credit card transactions. And it looks like a little handheld calculator, basically. And so you take this cap reader, and let's say you want to go pay for something online. You take your card, you put it in there, right? And then you enter your PIN into that cap reader. Now note that because that cap reader comes from MasterCard, abstractly speaking, and because it can't be updated with stuff that the user installs, MasterCard trusts that cap reader to not have malware, right? So that avoids the problem of keyloggers and stuff like that. So you put your card in there, you enter the PIN to this trusted terminal, then it's basically going to output some 8-digit code. And that's the code that you actually use to tell the web service, hey, I am who I say I am with respect to this particular card here. So that's sort of the physical setup of how you use it, okay? So what does that longer version of the paper say about the cap reader? So they say it's pretty easy to learn because you just stick your card in there, enter your PIN, kind of like you would do it in ATM. That all works fine. For infrequent errors, they say quasi-yes for the same reason that they say quasi-yes for passwords, because entering your PIN, sometimes you might make a mistake or something like that. It is not scalable for users because you basically have to have a separate credit card, a separate PIN, maybe even a separate cap reader for each site that you go to. So it says no for scalability. Easy recovery is no, right? How do you replace a lost cap reader? How do you get a new card? That's kind of a pain. And it also fails nothing to carry because you've got to carry your card in the cap reader. So this is not server compatible because the site has to know how to use this special cap reader protocol before it can proceed. It is browser compatible though, because you're just using standard HTML, CSS, and JavaScript to interact with the backend. And the authors say no, it's not accessible because blind people can't easily read that 8-digit code that's put out by the cap reader. So what happens next? So for the security questions though, this thing just dominates, right? So for every single one of these, it's a yes, right? So in particular, these 8-digit codes that are output by the cap reader, they're one-time codes, right? So every time you have an online transaction, it'll spit out this unique thing that will never be used again, right? And so what's nice about that is that means, for example, that it's resistant to physical observation, because if I see you generate a particular 8-digit code, I can't use that again, right? It's not a static token like a password, right? Similarly, it's resistant to throttled and unthrottled guesses because these things just get thrown away, right? So even if I leak one of these things to you, you can't then use it to impersonate me. Why is it resistant to leaks of that 8-digit code from other services? It's a one-time thing, once again. So anyways, so the cap reader just runs the table on all these security properties, and yet people don't use cap readers in practice, right? They're not a super popular thing. And so why does that happen? Well, once again, and in fact, one thing I forgot, so if we're looking at my little sort of qualitative number score, right? So cap readers get a 10.5, right? And so this seems great, particularly because it runs the table and all these things here. But once again, why don't we use these things? Well, because in most people's lives, there's a bad trade-off here between the security and then the usability and the deployability. People don't want to carry on cap readers. People don't want to go through this whole protocol of I got to put the thing in here and then get this digit and then sort of put this digit into the website. And so what this means is that in practice, deployability and usability are oftentimes more important than security, right? Because developers don't want to go to the cost of integrating these new mechanisms into their services. Users don't want to have to learn how to use these things. And if users are given any freedom whatsoever to choose the security of their scheme, they will often pick small passwords or weak pins or things like that. And so there are some situations where things like cap readers or smart cards or things like that make sense. So for example, in corporations, for example, like a lot of tech companies require you to have a smart card to get into buildings or things like that. Also, like if you're in the military, then you basically get told what to do, right? So if you're in the military, it might make sense to have one of these hardware-based schemes, or even some of these sort of paper printout type schemes, like the military codebook type schemes. But in most cases, those things are going to be rejected by regular users. So the take-home point is that when you're considering these security schemes, you can't just consider sort of the raw security of them. You also have to consider the usability and deployability story. All right, that's it. See you guys next Monday.